So I want to continue talking about our dynamic programming squared formulation of a Ramsey plan in our linear quadratic version of Calvo's. And so just to, I don't want to clarify something um, and interpret what I said at the conclusion of the last lecture. So just to kick things off, remember that we had this definition of this set omega of theta zero. So it's a set of what? It's a set of continuation thetas and entire plans for money creation from zero to infinity. But the thetas and the mu's have to satisfy this difference equation, which is the backward-looking version of the law of motion for that connects inflation to money creation. And this is an unstable difference equation, but we're going to define this set. Um, and then I define something called a continuation Ramsey plan. And again, finding the state is an art. So the key thing here is, first we defined the value function for a continuation Ramsey planner who has state variable theta zero. And theta zero is an initial inflation rate that the continuation Ramsey planner at time zero has to deliver. Has no choice about it. Now he can deliver it in any way he wants. And remember, there's all sorts of money creation paths that will deliver that. And that was an insight that I got from reading Chang's paper. So among all those, the equivalence class of mu processes that will support theta zero, the continuation Ramsey planner stuck with theta zero wants the one that maximizes this criterion. So we stare at this and we Bellmanize it. We convert this problem in sequences into a dynamic programming problem that involves a state today, a control today mu, and a choice of a state tomorrow theta prime that maximizes this. Now here's the continuation value function for a continuation Ramsey planner who's going to be stuck with theta prime. So today's continuation Ramsey planner is choosing a theta prime to stick next period's continuation Ramsey planner with. That's a trick. And theta prime has to satisfy, well, this difference equation. And so this is a Bellman equation. It looks like an ordinary Bellman equation. Well, here's this difference equation, which is explosive, but because we have this control, we can stop the explosion. So this is a Bellman equation. There's a value function on the left and the right, and we solve for a fixed point. And then indeed, J of theta is going to satisfy a Riccati equation. You could show that, and we'll come back to that. So this is a continuation Ramsey problem. That's its value. Now, it's not a Ramsey problem. So the Ramsey problem is going to be this: at time zero, there's the Ramsey planner's problem is this: he or she has to find a theta zero that he chooses to hand to the time zero continuation Ramsey planner. So for the Ramsey planner, theta zero here is not a state for the Ramsey planner, because he gets to choose that. Because remember, he's choosing the entire sequence of money creation rates, and therefore the entire sequence of inflation rates. He wants to choose the entire sequence. So we've broken the problem into two parts, a continuation Ramsey planner, and then the Ramsey planner, well, he's just going to choose the theta zero that maximizes this. So the value of the Ramsey plan is going to solve this. So this is the Ramsey planner's problem. So when I said last time, at the conclusion of the last little video, that the continuation Ramsey problem is not the same as the Ramsey problem, that's what I meant. And essentially, if you think hard about that, that's embedded in that the difference, the discrepancy between the Ramsey planner's problem and the continuation Ramsey planner's problem is the essence of this, the time inconsistency that Calvo discovered in his classic paper. So now what I want to do is I want to turn to this second note about the Ramsey plan, and we're going to drill down and we're going to use dynamic programming or dynamic programming squared to solve the Ramsey problem. And we're going to talk about some other things, Markov perfect and another equilibrium concept. So that's what we're going to do. So this second paper is it's a sequel to our machine learning paper. So what we're going to do is, again, we're going to use insights of Chang and dynamic programming squared. We're going to compute an optimal plan via Bellman equations for, well, there's going to be two Bellman equations. One for the government's continuation value, and the other for promised inflation. And another thing we're going to do in this kind of a reader's guide to this little note, we're going to explore how alternative timing protocols for the government decision-making affect outcomes. So, okay, I'm going to go fast over this because the model is exactly what we talked about last time. The model is exactly what we handed to the machine computer in order to do machine learning. Here's our cast of characters, P, M, theta, mu. There's no uncertainty, exactly the same. It says demand for real balances, just a warmers, exactly the same kind. So I'll just skip over this. There's this. Now, what we're going to do is now this problem was all rigged, and you'll understand why we rigged it, because linear quadratic dynamic programming is really easy. It's fast to compute. So what we're going to do is we're going to represent this difference equation as a linear state space system. So our state vector is going to be 1 in theta t. Our control is going to be mu t. And this is the evolution equation that describes theta t, and that we're going to stick the continuation Ramsey planner with this. And we're going to write it as a state space notation. So I'm kind of assuming as background linear quadratic dynamic programming. So where here's our state, here's our A matrix, here's our B matrix. I just stare at this. So now, we've remarked at this before. This A matrix is unstable on eigenvalues greater than 1, but that's not a problem because the Ramsey planner is going to want a decision rule for mu that's going to stabilize this system. That's what linear dynamic programming is all about. And so it's going to render this theta sequence square summable. Okay, so there's our government objective function, exactly the same as before. We can go over this quickly. I'll notice the following thing. We could have a little fun with this model, and we could say, according to this criterion function, this utility function that we made up for the representative consumer, we could compute, what Milton Friedman would do is the bliss level of real balances, because this is a specification where, because it's quadratic, there's a maximum to this utility function, and associated with that, there's a maximum utility maximizing inflation rate. And this is the kind of Friedman optimum rate of inflation in this model. So Milton Friedman would look at this if he accepted the approximations, and he'd say, well, the government should destroy money at this rate. It should withdraw money to generate deflation at that rate. And that's kind of where Calvo started, because he said, Friedman's right. If there's no distortion costs of destroying money at this way. But he said, well, Calvo said, the way you withdraw money is you got a tax, and that's typically distorting. So he added that distortion, and that's how he got his model. So, we went over this earlier when we were setting up our machine learning problem. So now we're just going to do this with dynamic programming. We're gonna make concrete that J function we had. So this S function that we had before down here, I'm going to convert that S function into an R function. I'm going to flip signs because my linear regulator problem is I think it's a minimum problem, but that's just a convention. So I'm going to define my criterion function as a quadratic form in the state, and a quadratic form in the control. And here's my R matrix, that quadratic form, and my Q matrix is that. So I'm getting ready to hand this over to a Python linear quadratic dynamic programming problem. So if I do that, I get I can write the like we did before. I can write the continuation value like this. Just this is all what we did before. I can write it like this, and then I can. I'm kind of all set up to do my analysis. So, so now we're all set up, and we're going to talk about different timing protocols now, because we're going to perturb Calvo's model. We're going to make different assumptions about timing protocols. So we're going to talk about what a policymaker chooses. Does it choose a sequence, or does it choose a single mu-t? And then the question is, when does it do it? Does it do it once and for all at time t, or does it do it periodically or various times at particular t's? And then we're going to talk about assumptions, impacts about expectations, how mu-t influences expectations about past and future inflation, Remember, mu-t, the whole point of source of subtlety in Calvo's model is that mu-t influences past inflations. Okay, so let's talk about a couple timing protocols. The Ramsey or Stackelberg timing protocol is that a single policymaker at time 0 chooses this entire sequence and then walks away. It's a static problem. An alternative, quite popular timing protocol, and keep every other aspect of the model the same, but we're going to change the timing protocol. That's going to change the model. We're going to have a sequence of policymakers indexed by t equals 0, 1, 2, and 3. So So they're really going to choose, and they're going to choose on their own. So each policymaker is going to set mu t at time t, focusing only on the continuation value vt. That's all it's going to focus on. Now, this is worth thinking about what I have here, because when I Bellmanized the Ramsey problem before, last time, and I had a Ramsey planner and a continuation Ramsey planner, you could say, wait a minute, did I really have a single policymaker? And I want to claim, yes, I did. So that continuation Ramsey planner is a virtual thing that's we put in to represent the Stackelberger Ramsey plan recursively. But everything was happening at time, that the continuation Ramsey planner was imaginary, really. It was a device to represent the plan recursively. So I want you to think about that. Okay. So I'm going to describe three models. See a big typo here. We're going to have a Ramsey planner. We had what we had talked last time. We have a constrained to a constant Ramsey planner. It gets to choose this entire sequence, but the sequence can't vary over time. It's just boring. So mu t has to be a mu bar. And then we have Markov perfect equilibrium. And these are three different concepts. So the equilibrium here is essentially think of it as a game being played among a sequence of policymakers. So we're going to have independent policymakers for each t, and each policymaker assumes that future decisions are independent of its choice. This is critical. This is critical. It's one of the defining features of a Markov perfect equilibrium. And later we'll tamper with this assumption. Okay. So we're all equipped to quickly go over a Ramsey plan. So the Ramsey planner chooses what we had, subject to law of motion. Again, I split that into two stages. So this stage one, we take the initial inflation rate as given. That's the key thing. It's given. And we solve what looks like an ordinary linear quadratic discounted dynamic programming problem. And then stage two, we choose an optimal initial rate of inflation. That's what I sketched before. And let's see how that does. So the way we do that is, well, we're just going to rewrite the math that we had in terms of defining this set. We're going to have a set omega of x0, and we're going to require that this continuation sequence that's going to have to belong to us. They're all the sequences are going to have to be square summable. You square xt plus 1, you square it, and you add up over all t's. We require that be finite. Okay, we define that set, and now we have this. I'm kind of abusing notation. Instead of calling it j of theta 0, I'm going to call it j of x0. Of course, x0 is just a constant 1 and theta 0. So there's my Max problem. And there's my Bellman equation. But this just looks like a linear quadratic control problem. And we can deduce what the optimum value function is. It solves the Riccati equation. And so we can guess that j of x is a quadratic form in P. And if we substitute this into the Bellman equation, we'll get a matrix Riccati equation for P, and we'll get an associated optimal decision rule. Mu t is going to be equal to minus fxt, function of the state. This is just linear control theory, dynamic programming, and f is going to look like this. We get almost a closed form formula for f. Almost, I say we have to solve this Riccati equation, but Python does that easily. And then we get this value function vt that looks like this. Vt is quadratic, just like we discovered with our machine learning. There it is, Vt. Turns out those coefficients in Vt are related to the coefficients in the value function that we had on the previous slide here. So the Ramsey plan, what's the Ramsey plan? It's going to be to set mu t according to this. So now we have our Ramsey plan, and we have an updating rule for theta t. That's easy. We just compute a minus bf, as we usually do when we're computing a closed loop for linear quadratic dynamic programming. And then the only thing that's left for us, just like before, is we have to have the Ramsey. So we've solved the continuation Ramsey plan. We know what the continuation Ramsey plan is. Got that updating rule. Remember, that's what we discovered with machine learning. So we're sure that now the Ramsey planner, continuation Ramsey planner, wants to stabilize the system, and that comes from these theorems in linear quadratic dynamic programming. And now all that's set is we have to have the Ramsey planner choose theta 0, and well, that's our problem, and so we have to solve this problem. This is just a quadratic, and so we can compute theta 0 equals theta. It's just the ratio of these two elements of the value function for the linear quadratic programming problem. It's beautiful. So now we've represented a Ramsey plan recursively. We've got this initial condition. You got to start it out, initial state, which the Ramsey planner chooses, and then here's our formula. And we discovered all this with machine learning. But here we've learned a lot about the structure and how hard we have to work to make it recursive. So now we can kind of sit back and do a little philosophizing, and we'll notice that the sequence theta t, it represents, through the lens of the continuation Ramsey plan, these are promised inflation rates. What do we mean by that? These are problems that the continuation Ramsey planner, he's stuck with a theta t. He hands a theta t plus 1 to his successor. And that's a promised inflation rate that continuation Ramsey planner promises for the future, and the continuation, the successor continuation Ramsey planner is obligated to honor that promise. That's why we call this. This is Chang's notation. So these generate money growth rates, mu, a whole sequence that produce actual inflation rates that are equal to the promised rates. So under a Ramsey plan, promised inflation equals actual inflation. And what you'll notice here is, it's kind of evident from thinking hard about the Calvo problem, is Calvo's problem, builds heavily on rational expectations. You can ask why, and if you read Calvo's paper, he talks about how earlier papers bringing, just a few years earlier, bringing rational expectations in the macro helped him set up his problem. You drop rational expectations. His problem, kind of big problem, is that it gets confused or evaporates. Okay, so now we completely understand the dynamics under this, and we've discovered this. So the variation over time in the continuation value, the theta and the mu, are symptoms of time inconsistency. So we talked about that when we did machine learning. So now we'll go just to set up some interesting Python that we can experiment with to learn more about this model. We can quickly describe how we're going to compute a constrained to be a constant growth rate Ramsey plan. Well, we can actually solve that by hand. If we set up that problem, the Ramsey planner's problem is he just has to choose a scalar. So it's the problem with a sequence gets replaced by just choosing one number. So it's a quadratic problem, and we can compute it by hand. So this is the constrained optimum, constrained to a constant Ramsey plan. So we can compute the value function quickly. So, and now what I'm just going to quickly do is show you. So there we got constant. There's no time inconsistency, or we forced there to be no time variation. So here's another way people, in effect, force it. It's an alternative way. And you should ask, is it a better way or a worse way? And you should ask, what do I mean by better or worse? Or what do you mean? So the setup is Markov perfect. There's going to be a sequence of policymakers indexed by time. At time t, a government's going to choose mu t any way it wants, and it's going to expect all future governments to set mu t plus j equal to mu bar. So it thinks that all future governments are going to do the same. That's key. This is all going to be hinged on beliefs. So it thinks that. So when a government sets mu, it believes that mu bar is unaffected by its choice. It's going to take this as given. That's key. It thinks it chooses mu independently, even though in the end, it's going to end up choosing the same mu that everybody else does. So under this assumption, what theta t is, it's a weighted average of what I set this today and what I think my successors are going to set it. They're all going to set the same thing. So here's what theta t is under this timing protocol. This is under a timing protocol and a belief protocol. So when I do that, the Markov perfect government's problem is at given mu bar, the time t government solves this problem, easy problem. And then, so this is like an exercise to do. And then if you do this, you can actually compute this by hand. So you can get a best response map. When I expect the future mu bar to be mu bar, I set mu equal to mu t. And then a Markov perfect equilibrium is going to be a fixed point of this function f. And here's the function. We can compute it. That's this math that I showed you here. It's just this univariate optimization problem where mu bar is a parameter. And then you can compute the fixed point. So a Markov perfect equilibrium is a fixed point of this best response map. There's the definition. And we can calculate it. There it is. And there's the value of the Markov perfect equilibrium. So now what we have is we have kind of three timing protocols or ways of completing or altering Calvo's model. We have the original Calvo problem. We have the constrained to a constant mu, and we have our Markov perfect. So the way I want to conclude this little session is I want to look at the outcomes. So I'm going to compare outcomes. We're going to, under a standard Ramsey, Markov perfect, and a Ramsey plan in which we're restricted to choose a time invariant mu. So I want to show you. So I want you to look at this little paper or the accompanying quant econ lecture, and I want you to stare at some graphs. So here's mu t and theta t plus 1 as functions of theta. And when you look at this, I want you to look at what these are. Theta star, that's Friedman's optimum quantity of money. Theta m per Markov perfect equilibrium is here. Theta constrained to Ramsey is here. I'm sorry. Theta, the initial theta chosen by the Ramsey planner is here. The eventual theta, the limit of the so-called timeless perspective is here, and the constrained to Ramsey is here. So I want you to look at this graph, and then this graph kind of shows us the dynamics under the Ramsey plan, and okay, and then what I want you to do and think about the economics. I want you to compare the thetas. So it turns out that theta 0 is less than the Markov perfect equilibrium, and theta 0 infinity is less than. Look at this ordering. I want you to stare at this and try to interpret it and understand it. So this, which you can stop this video or you can look at the slides or the accompanying the paper. This has lots of the results. And then here's a killer graph. In the quant econ lecture, we do lots of things with this graph, but here's J of theta. That's what we talked about last time. That's the continuation value, the continuation Ramsey planner's value function. What V of theta is, that's something else. That's the continuation value function. And this dotted line, this thing is the value associated with a constant to Ramsey. And I'm going to conclude this by saying, I'm going to invite you to stare at this and interpret it and look at these numbers of on this axis, we have the inflation rate. So with this, I've kind of opened up a reader's guide to this quant econ lecture or the little paper.